Hello everyone, I am Harith Reddy, working for St. Peter's Engineering College in the Department of Computer Science and Engineering. In this session, let us discuss about Push Down Automata. So, Push Down Automata is an extension of finite automata. So, in finite automata, there is one problem. The problem is with memory. So, Push Down Automata is an extension of finite automata. In finite automata, there is a problem of memory. Finite automata cannot remember long sequence of logics. For example, if you consider finite automata, this finite automata cannot recognize a language L is equals to A power n followed by P power n, where n is greater than or equals to 1. This logic is not implemented by using finite automata, because in finite automata, if you consider a input tape is an area where your information or a string is stored. L equals to A power n B power n, it indicates that equal number of A's are followed by equal number of B's. For example, if I want to store 2 A's and 2 B's, okay, so the memory is finite here. Finite is countable, so that is the reason I have taken a very short string. Now if you are observing this logic, equal number of A's are followed by equal number of B's. Initially the tape head will be here. After reading A, the head will be moving one direction in a right side. Then after reading A, it will be coming to this position, let us assume. So here in this finite automata, whatever it has read earlier, that means it has read 2 A's earlier, this A's whatever it has read, it is going to forget. So in order to overcome that problem, we are going to use a concept of a push down automata. So the short form of push down automata is PDA. So this push down automata is nothing but finite automata plus a stack. Finite automata plus a stack is called as a push down automata. So this stack is acting like a memory where we are going to store some inputs and we are going to retrieve the data. Now before going to in-depth discussion of push down automata, let me give you the differences between a finite automata and a push down automata. So in finite automata, if I am going to consider, so this finite automata is a 5-tuple machine. Finite automata is a 5-tuple machine. Those 5 tuples are capital Q, which indicates set of states. Sigma is a input alphabet. Next one is transition function, which is denoted by delta. Next one is Q naught. And next one is capital F. So any finite automata, if you consider, this 5 tuples should be there in that finite automata. If any one of them are missing, then you are not calling it as a finite automata. Okay, now let me consider a push down automata. This push down automata is an extension of finite automata. So this push down automata will be having 7 tuples. If you are observing this logic here, so there is something which is common in push down automata and finite automata. So whatever the 5 tuples are there in this finite automata, same will be there in push down automata also, which are capital Q, sigma, transition function, Q naught and capital F. Along with that, there are extra 2 tuples. The 2 tuples are stack tuples. One is stack alphabet and next one is top of stack symbol. So these are the 7 tuples in a push down automata. So the reason behind saying this logic is that there is similarity between finite automata and push down automata. If you understand the concept of finite automata, then only it is very easy to understand push down automata. So these are the for example, what does capital Q here indicates? Capital Q here indicates set of states. Capital Q here indicates set of states. Okay, likewise sigma here indicates set of input alphabets. Set of input alphabets. Likewise, delta here indicates transition function. Delta indicates transition function. Delta indicates transition function. Q naught is a initial state. Q naught is initial state. So every finite automata you consider, there will be a single initial state, because that initial state will represent the starting point. And a finite automata can have any number of final states. So that is the reason I am going to write set of final states. So capital Q indicates set of states, sigma indicates set of input symbols. Here delta indicates transition function, Q naught indicates initial state, and F indicates set of final states. So a finite automata can have a single initial state and any number of final state. If you are observing this logic here for push down automata, all these 5 tuples are common. So I would like to only mention about this tau. This reverse L symbol is called as tau symbol. So tau, which is a stack alphabet, this is a stack alphabet, and Z0 indicates the top of stack value. Z0 indicates a top of stack value. Okay, so this is the basic differences between a finite automata and a push down automata. Is it clear? Now I'll explain a concept of push down automata by taking a stack. I'll take a language and I'll see how I'm going to implement that language here now. Now I am taking an example for push down automata. Now I am going to construct a push down automata which accepts the language L is equals to A power n B power n, where n is greater than or equals to 1. So he will give you that language and ask you to construct a push down automata. First, what is the thing that we have to do is to generate a strings from that language. The strings are normally denoted by letter W. So from this language I am going to derive some strings. For example, if n is equals to 1, I'll take an example now. For example, if n is equals to 1, what is the string that can be generated? Okay, well, if n is equals to 1, what is the string that can be generated? So the string that is generated is AB. So I'm substituting 1 here, a power 1 and b power 1, which is AB. For example, if n value is equals to 2, the string generated is a square b square. This I can write it as double A followed by double B. For example, if n is equals to 3, the string that is generated is a cube b cube. This I can write it as triple A followed by triple B. So likewise, if you are substituting the n values, the string will be generated continuously. Okay, now if any, I am going to represent all these strings in the form of a set. First I am going to write AB because this indicates the string when n value is equals to 1. Next one is a square b square, that is double A followed by double B. Next one is n is equals to 3. If n is equals to 3, I am going to write triple A followed by triple B, so on and so forth. So this is the string that I am going to get generated. So now after observing the string, let us come to a conclusion. That is the first and foremost thing that we have to do. So I am going to write some logic. First of all, I am going to write some logic. What is the logic is that when A's are encountered, so just before I have said you, so this push down automata is going to maintain some stack. Push down automata is going to maintain a stack. For example, let me consider that this is my stack. Okay, so this is my stack. So what is the logic I am going to employ is that when A's are encountered, while reading the string, I'll push that information onto the stack. A's encountered, I am going to push that information on stack. If B's are encountered, I am going to pop the value of A from the top of stack. This is the logic I implement. When A's are occurring, I am going to add that A's onto the stack. When B's are occurring, I am going to pop the respective top of stack value A from the stack. Okay, now I am going to construct a push down automata now. If I am observing this language, so that language is definitely starting with A. So what I am going to do means I am going to construct a push down automata here. So I am going to start from the initial state, which is Q0 is my initial state. So if I am observing this, definitely it is starting with what? A. So when A's are encountered, when first A is encountered, if I am observing the top of stack value here, nothing is there. So blindly I should push what? Z0. This is a rule. I should insert Z0 onto the top of stack because this Z0 is acting as the marker. This Z0 is acting as the marker. It is acting as an indicator. So whenever you are popping the values from the top of stack, when Z0 is encountered, it means that the data which is there below this Z0 is not useful for us. So it is acting as a hint. So when A is there, okay, so when first A is encountered, so nothing is there on the top of stack. So nothing is there means I am going to write here epsilon. So when first A is encountered, nothing is there on the top of stack. Still I am going to add Z0 onto the top of stack. So this is your input value. Second one is your top of stack value, and third one is what you are performing an action. So initially your top of stack value is epsilon, but still you are inserting what? Z0. This is new top of stack value. This is for our indication. So I am going to add Z0 onto the top of stack. So 1 minute. Okay, I'm going to take an example now and I'm going to prove it now. So initially I am starting from Q0 state. This Q0 is known as an initial state. So here I am going to write the transitions now. First here epsilon, assume that there is no input at all and nothing is there on the top of stack. Initially your top of stack is empty. You don't have any input and your top of stack is empty. Still you are going to add Z0 onto the top of stack. This is the logic in the push down automata. I don't have any input, nothing is there on the top of stack, and I am going to insert what? Z0. Here this first here epsilon indicates it is input. Second epsilon indicates it is the previous top of stack, and third Z0 indicates that it is a new top of stack value. Then after integrating Z0, this Z0 is acting as a marker or an indicator. Now I have reached to a state called Q1 after some point of time. If I am observing this logic, definitely it is starting with what? A. So assume that my input is A, and on the top of stack what is there? Z0 is there. So I have employed a logic. When A's are encountered, I should push that A onto the top of stack. So I am going to write here A Z0. That means along with Z0, I am going to add A. Whenever you are performing pushing operation onto the top of stack, on right side there will be two symbols. If you are observing this logic, no A is there here. 1A, 2A's, 3A's, so on and so forth. It means that here I can write a self loop. Let any number of A's might encounter. The top of stack value will be definitely what? A. I am going to push this A onto top of stack. I can write AA. So this is what the logic is involved. First, it should be definitely starting with A, and if I am observing the logic, it can be 0 repetitions of A, 1A, 2A's, and so many A's. That is the reason I have written self loop here. So definitely I am going to add that A's onto the top of stack. This is the logic that is involved. Now, at certain point of time, definitely first B will occur. Here first B is occurring. On the top of stack, what will be encountered? Definitely on the top of stack, this is your top of stack. On top of stack, definitely A's will be encountered. So what I have to do now, for every B I should pop one A from the top of stack. So popping is nothing but removing that A from the top of stack. Now if I am writing 3A's here, definitely 3 B's will be encountered. When first B is encountered, I am going to pop that A from the top of stack. Yes, I have popped it. Now my top of stack is pointing out here. This is my top of stack value now. This A is my top of stack. So popping is returned by using epsilon at the right side. Popping is represented by using epsilon at the right side. So when first B is encountered, definitely on the top of stack it will be A, and I am going to pop it. Popping symbol is represented by using epsilon. Whenever you are pushing the information onto top of stack, there will be two symbols on the right side. Whenever you are popping some information on the top of stack, you should write epsilon on the right side. Now if you are observing, so any number of B's might occur. Now look at here. So 0 B's, sorry, 1 B followed by 2 B's followed by 3 B's, so on and so forth. So here if I am observing, any number of B's might encounter. Assume that this is second B. Definitely on the top of stack what is there? A. So what I am going to do now, I should pop it. So for second B also I am going to pop that A from the top of stack. Again when third B is encountered, on the top of stack there is A. So again what happens? This A will be popped out. This is the logic here. Still you are at Q2 only. Now at certain point of time you will reach to the end of the input. That means all B's are encountered, nothing is there. That means at certain point of time, so I don't have my input, and on the top of stack what is left over? Z0. So this Z0 will be acting as an indicator for us. This Z0 itself indicates that the data which is present below Z0 is not required. So I am going to pop it also. If I am going to pop it, I am going to write it by using what? Epsilon. So after that I am reaching to what state? Final state. So this is a push down automata. Now finally I am going to remove this Z0 also. This procedure is known as acceptance of push down automata by empty stack. Acceptance of push down automata by empty stack. If you are keeping z0 as it is on the top of stack, it is called as acceptance by final state. So this is acceptance by empty stack. This is acceptance by empty stack. Now the procedure which is known as instantaneous description, which says that whatever you have drawn is right or not. There is a procedure to check whatever you have drawn is right or not. That procedure is known as instantaneous description. Now I am going to write a instantaneous description. Instantaneous description. It is a method which is used to prove whatever you have drawn is correct or not. Instantaneous description. Now in order to prove the instantaneous description, let us try to take some valid string from the language. Now if you are observing the language, you can take any valid string. Okay, now if I am going to take some string called AABB, so I am going to take a string called AABB. You should always take a valid string in order to prove the instantaneous description. AA followed by BB. So this is the input. This is the input symbol. Now definitely you should start from the initial state. What is the initial state here? Q0. Initial state is Q0. Next, assume that initially nothing is there on the top of stack, which is epsilon. So Q0 is an initial state. So this is your input and this is a top of stack value. Now if you are observing here, sir, adding epsilon in front of input does not change the meaning of that input. So epsilon is called as null string. Always if you want to prove the instantaneous description, blindly add epsilon at the beginning of the input. Now look at this diagram. Q0 epsilon epsilon. So Q0 on epsilon epsilon, you are directed to what state? Q1. So here I can write Q0 epsilon epsilon is Q1. Okay, so I am directed to Q1 state. The remaining input is what? AA followed by BB. Initially on the top of stack it is epsilon, but now I am adding what? Z0. Now this is the thing we have to concentrate now. Q1, A and Z0. On Q1, A is the input and Z0 is the top of stack value. You are directed to Q1 state. This is Q2, this is Q3 and this is Q final. A Q1 on A, you are directed to Q2 state. So here I am directed to Q2 state. Now the remaining input is ABB. Now what action I am going to perform here now? Pushing operation. So along with Z0 I am going to add what? A. Now Q2 A and A. Q2 AA. For Q2 state, if you are giving A as an input and A is the top of stack, you are still in Q2 state and you are pushing that A onto top of stack. Now I am still in Q2 state. The input is what? BB, and I am going to push whenever I am performing push operation. So two symbols will be there on top of stack. So I am going to add AAZ0. Initially this was your previous top of stack value. Now this is the new top of stack value. Now Q2 B and A. Sir, for Q2 state, if I am giving BA, I am going to Q3 state. I am reaching to Q3 state. Epsilon here indicates popping. So what I am going to do now? I am going to transition for Q3 state. Remaining input is what? B. and epsilon indicates I am popping it. Now the remaining input is what? AZ not. Okay, now you are going to give Q3BA. Check the transition for Q3BA. So Q3 on B and A, again you are going to pop what? The top of stack element, because I am writing epsilon there. So I am directed to Q3. The remaining input is epsilon, and leftover in top of stack is what? Z0, because this should be popped out from the top of stack. When B is encountered, I am popping A from the top of stack. Now Q3 epsilon Z0. Q3 epsilon Z0. I am reaching to Q final state, and I am popping this Z0 also because I have returned epsilon there. So I am reaching to Q final state. I don't have any input. I am popping this Z0 from top of stack. Now this is called as acceptance by empty stack. Acceptance by empty stack. So that means whatever the push down automata I have drawn is correct, and I have proved the answer also. Now let me recap the concepts for 2 minutes. Now push down automata is an extension of finite automata. Push down automata is a finite automata plus stack. So in a finite automata, the memory is limited. So this finite automata cannot remember long sequence of logics. In order to overcome that, we are using a push down automata. Here we are going to maintain a separate memory called as stack memory. So if you are observing this, a finite automata contains 5 tuples and push down automata contains 7 tuples, where 2 tuples are extra. These 2 tuples are related to a stack tuples. One is tau symbol and other one is Z0. Tau indicates this tau indicates a stack alphabet, and Z0 indicates top of stack. Q indicates set of states, sigma indicates set of input symbols, delta indicates a transition function, Q0 indicates initial state, and F indicates set of final states. Whether it might be a finite automata or a push down automata, so there should be a single initial state and any number of final states. Now I have taken an example of a push down automata, which is L equals to A power n B power n, where n is greater than or equals to 1. Here L is a language which is deriving a set of A's and set of B's, where A's are equal number of A's are followed by equal number of B's. So this is the logic which derives equal number of A's followed by equal number of B's. So the logic I have assumed here is that I am going to maintain a stack. When A's are encountered, I am going to add that information onto stack. For when B is encountered, I am going to pop respective A from top of stack value. So this is a diagram for a push down automata. As I said, push down automata has a single initial state and any number of final states. It can be one or many. So here I don't have any input, I don't have a top of stack, still I am pushing Z0. This Z0 is acting as a marker. So if you are observing this logic, when A is encountered, definitely on top of stack there is Z0. If I am writing 2 symbols on the right side, it indicates that I am adding. So here I have reached here. Now second A is encountered, and the top of stack there will be A only. I am going to add it. So that means I have taken 2 A's followed by 2 B's logic now. So when first B is encountered, so top of stack value is A. First B is encountered, top of stack value is A. I am going to pop it. I am going to pop it, and I am going to reach it to Q3 now. So I'm going to pop it. For every B, I'm going to pop one A from top of stack. So here when second B is encountered, so I am going to pop that A from top of stack. Yes, I am popping it. So lastly, I am reaching the end of my input and z0 is left over. I don't have any input with me now. I don't have any input. My top of stack is z0. I am going to pop that z0 from top of stack. This is called as acceptance by empty stack. So this is an instantaneous description. This instantaneous description is a method which says whether whatever you have drawn is valid or not. So if you are taking a valid string, definitely your push down automata should accept it. Thank you.